In this video, we are going to look at the 3D shapes of orbitals. The shapes of the orbitals mainly determined by the angular momentum quantum number L. Different angular momentum quantum number L value will give us different shape of the atomic orbitals. For example, with the principal quantum number n equals to 1, the only allowed angular momentum quantum number L is equal to 0. With L value equals to 0, basically it means that the orbitals in the subshell should have the spherical shape. With principal quantum number n equals to 1 and angular momentum quantum number L equals to 0, basically it means that the subshell should have the designations of 1s. For L equals to 0, there is only one allowed magnetic quantum number m value, which is m equal to 0. As only one magnetic quantum number value can be written for L equals to 0, basically it means that in the 1s subshell, there is only one orbital, and that one orbital having the spherical shape. So how to draw the orbital? First, we draw the spherical shape, and then we draw the s-axis, we draw the y-axis, and then the z-axis. So this is the one orbital in the 1s subshell which having the spherical shape. For principal quantum number n equals to 2, there are two allowed angular momentum quantum number value, which is L equals to 0 and L equals to 1. For L equals to 0, basically it means that the orbitals in the subshell having the spherical shape. While for L equals to 1, basically it means that the orbitals in the subshell should have the dumbbell shape. As we know that L telling us the shape of the orbitals, and different L value giving different shape of the orbitals. For n equals to 2 and L equals to 0, the subshell should have the designations of 2s, while for n equals to 2 and L equals to 1, the designations of the subshell is 2p. For L equals to 0, there will only be one allowed magnetic quantum number, which is m equals to 0. Since only one magnetic quantum number can be written for L equals to 0, means that in the 2s subshell, there is only one orbital present, and that orbital having the spherical shape. So when we draw the spherical shape orbital in the 2s subshell, we should draw it bigger than the 1s subshell. Why bigger? Because the principal quantum number n is equal to 2. When n is equal to 2, it is bigger than the n equals to 1. When it is bigger, means that the orbital in the 2s subshell will have bigger size and energy than the orbitals in the 1s subshell. So to draw it, first we draw the spherical shape, and then we draw the s-axis, and then we draw the y-axis, and then we draw the z-axis. So this is the one orbital in the 2s subshell having the spherical shape. For L equals to 1, the orbitals in the subshell will have the dumbbell shape. For L equals to 1, there are three allowed magnetic quantum number values, which is -1, 0, and +1. So as three magnetic quantum number values can be written, basically it means that there are three orbitals of different orientations in space in the 2p subshell. So how should we draw the three orbitals of different orientations having the dumbbell shape in the 2p subshell? So first we draw the dumbbell shape along the s-axis. Then we're drawing the y-axis and also the z-axis. So as this dumbbell-shaped orbital is lying along the s-axis, so therefore this orbital is called 2px. So this is one of the orbitals lying along the s-axis in the 2p subshell. So another orbitals will be lying along the y-axis. So to draw it, we draw the dumbbell shape along the y-axis, and then pull in the y-axis, and then draw the x-axis and also the z-axis. So as this orbital lying on the y-axis, so therefore this orbital is called 2py. So another orbital is lying along the z-axis. So to draw it, so first draw the orbital along the z-axis, and then draw the z-axis, and then draw the s and y axis. As this orbital lying along the z-axis, therefore it is being called as 2pz. So these are the three orbitals of different orientations in space in the 2p subshell, and they are having dumbbell shape. For principal quantum number n equals to 3, there are 3 allowed angular momentum quantum number, which is L equals to 0, L equals to 1, and L equals to 2. For L equals to 0, the orbitals in the subshell will have the spherical shape, while for L equals to 1, the orbitals in the subshell having the dumbbell shape, and for L equals to 2, the orbitals in the subshell having the shape of cloverleaf or donut. For n equals to 3 and L equals to 0, the designations of the subshell is 3s, while for n equals to 3, L equals to 1, the designations of the subshell is 3p, and for n equals to 3, L equals to 2, the designations of the subshell is 3d. For L equals to 0, there is only one allowed magnetic quantum number, which is m equals to 0. So means that in the 3s subshell, there is only one orbital of spherical shape. So how to draw the one orbitals in the 3s subshell with spherical shape? So again, we draw the spherical shape first. This spherical shape should be bigger than the shape of the orbitals in the 2s subshell, because now the principal quantum number n is equal to 3, which means that the orbital should have a bigger size than the orbitals in the 2s subshell. So first we draw the spherical shape, then we draw the s-axis, and then we draw the y-axis and also the z-axis. So this is the orbital in the 3s subshell, which has the spherical shape because the L is equals to 0. For L equals to 1, the orbitals in the subshell will have the dumbbell shape. For L equals to 1, there are 3 allowed magnetic quantum number values that can be written, which are m equals to -1, 0, and +1. As there are 3 magnetic quantum number that can be written, basically it means that there are 3 orbitals of different orientations in space in the 3p subshell. So one of the orbital is lying along the s-axis. So draw the orbitals of dumbbell shape. Now we need to draw it bigger size than the one in the 2p subshell, because now the principal quantum number is equals to 3, which means that the orbital should have a bigger size. So lying along the s-axis, and then draw the y-axis and also the z-axis. As it is lying along the s-axis, so this orbital is called 3px. Then another orbital in the 3p subshell will be lying along the y-axis. So having the dumbbell shape, must draw bigger than the one in the 2p subshell, because now the principal quantum number again is n equals to 3. So means that the orbital should have bigger size. So lying along the y-axis, draw the s-axis and also the z-axis. So as it is lying along the y-axis, so therefore it should be called 3py. So another orbital having dumbbell shape as well, but now need to lie along the z-axis. again need to draw it bigger size than the one in the 2p subshell, because now the principal quantum number n is equal to 3, means that the orbital is having bigger size. So draw the z axis, draw the s axis, and also draw the y axis. As it is lying along the z axis, so it should be called as 3pz. So all these three orbitals are having dumbbell shape because their angular momentum quantum number L is equals to 1, indicating that their shape is dumbbell shape. For L equals to 2, the orbitals in the subshell should have the cloverleaf shape or donut shape. For L equals to 2, there are 5 allowed magnetic quantum number value, which is m equals to -2, -1, 0, +1, and +2. So as there are 5 allowed magnetic quantum number that can be written, so basically it means that there are 5 orbitals of different orientations in space in the 3D subshell. So how should we draw these 5 orbitals of different orientations in space in the 3D subshell? So first, shall we draw 3D z square first? So for 3D z square, the orbitals is having the donut shape and lying along the z axis. So lying along the z axis, and then having a donut like this. And then we draw the x and y axis. So this is the 3D z square orbital having the donut shape. And then we can draw 3D x squared minus y squared. For 3D x squared minus y squared, basically the orbitals having the cloverleaf shape, and then it is lying on the x and y axis. So how should we draw it? So first we draw the cloverleaf, one side of the cloverleaf, so lying on the x-axis, and another side which is lying on the y-axis, and then we draw the z-axis. So this is the 3D x squared minus y squared orbitals which have the cloverleaf shape. And then we can draw 3D xy. So for 3D xy, basically the cloverleaf, the orbitals lie between x and y axis. So to draw it, first we draw the x and y axis. So the orbitals having the cloverleaf shape and lying between the x and y axis. So basically refer to this region, this region, this region, this region, and this region. And then the z-axis is piercing through the middle of it, like this. So this is the 3D xy orbitals. And then we can draw 3D sz orbitals. So 3D sz basically means that the orbitals having the cloverleaf shape and it is lying between s and z axis. So to draw that, first we draw the s and also the z axis, and then we need to draw the cloverleaf between the axis like this and like this, and the y-axis will pierce through the center of it, coming out like this. So this is the y-axis. So this is the 3D sz orbitals. And now we can draw the last one, 3D yz orbitals. So 3D yz orbitals basically means that the orbitals cloverleaf shape lying between the y-axis and also the z-axis. So therefore we draw the y-axis and the z-axis first, and then we draw the cloverleaf in between the axis. So like this. And then the S-axis pierce through the center of the axis and then coming out. So this is the 3d y z orbitals. So for all these 5 orbitals, they are having cloverleaf and or donut shape because their L, angular momentum quantum number value, is equal to 2. So indicating that their shape should be either cloverleaf or donut shape.